am Faiqeh, a postdoctoral research fellow at the CBSSP Center, University of Surrey, and today I will present our work, CoLeaF, a contrastive-collaborative learning framework for weakly supervised audiovisual video parsing. Audiovisual learning has emerged as a crucial field within computer vision, enabling AI systems to develop a better understanding of the world. Most audiovisual tasks assume the audio and visual data are temporally aligned. However, in practice, this assumption is not always valid. For instance, a car might run out of the camera's view. The audiovisual video parsing task instead introduces an unaligned setting for audiovisual learning, aiming to recognize and localize audible only, visible only, and audible visible events in a video. Since training a fully supervised model requires modality-specific, densely annotated data, making it a costly endeavor, this task is tackled in a weakly supervised scenario, where only video-level labels are available. To address this task, current approaches leverage cross-modal contexts, while the weakly supervised scenario is approached using multiple instance learning. However, we argue that while cross-modal learning is beneficial for detecting audible visible events, it can negatively affect the detection of audible only and visible only events by introducing irrelevant modality information. Additionally, since several actions can occur simultaneously in this task, current approaches propose to benefit from modeling the class relationships. However, this increases computational complexity. To overcome the mentioned challenges, we introduce CoLeaF, a contrastive-collaborative learning framework that relies on two network branches, reference and anchor. Reference focuses on unimodal data and their class relationships. Anchor incorporates unimodal and cross-modal context. Reference is used only during training to explicitly optimize the integration of cross-modal context in Anchor through an event-aware contrastive loss, and explicitly learn cross-relationships and transfer them to Anchor through a co-occurrence class knowledge distillation loss. Since only Anchor is deployed during inference, this allows the network to benefit from cross-relationships during training without adding a computational overhead during inference. Additionally, since the optimization process relies on the performance of reference, its effectiveness may diminish if reference is solely trained on weak labels. To address this without requiring additional annotations, Anchor collaboratively distills free modality-level knowledge for reference through a self-modality-level knowledge distillation loss. In the following, I will explain the details of our proposed losses. Event-aware contrastive loss adapts noise contrastive estimation to optimize cross-modal learning in Anchor, based on the event types present in the input video. The proposed objective encourages Anchor to learn embedding representations similar to those learned in reference, but the strength of the encouragement adapts to the degree of unaligned audible visible events present in the input video. More unaligned events lead to a stronger encouragement, while fewer unaligned events lead to a weaker encouragement. The unalignment degree is computed from the output predictions of the reference branch. To compute the self-modality-aware knowledge distillation loss, we first distill pseudo-labels from the estimated audio and visual event probabilities in the anchor branch. Then the labels are used by a binary cross-entropy loss to optimize the reference branch. The co-occurrence class knowledge distillation loss aims to transfer the learned class relationships from reference to anchor. To achieve this, it first computes the class correlations in both branches and then uses mean squared error to minimize the difference between them. Current approaches evaluate a method's performance by computing the F-score for audible only, visible only, and audible visible events separately, as well as their average and the overall F-score for all audible only and visible only events within each sample. To compute the F-score for audible only and visible only events, they compare the network's prediction individually with the audio and visual labels, while for audible visible events, they consider both modalities together. We argue that to accurately evaluate a method's performance on unaligned events, both modalities still need to be considered together. For instance, in this sample, consider T-1 segment. If we compare the audio prediction with the audio ground truths individually, it is considered a true positive for audible-only event detection. However, when both modalities are considered together, we observe that the network has detected that segment as audible visible, and it should be considered a false negative. To overcome this, we introduce audible-only and visible-only event proposals and ground truth labels, which are computed by considering both modalities and are used to compute the F-score for audible-only and visible-only events. We evaluate CoLeaF on two benchmark datasets, LLP and UNAV100, using the new metrics for unaligned events and the old metric for audible-visible events. The results show that CoLeaF significantly improves the state-of-the-art results by an average of 1.9% and 2.4% F-score on these datasets respectively. Our ablation studies also indicate the importance of different components and losses in CoLeaF's design. In this work, for the first time, we explore explicitly optimizing the integration of cross-modal contexts for the audio-visual video parsing task. We propose an approach that allows the network to explicitly learn class relationships without adding computational overhead during inference. We introduce novel metrics for the effective evaluation of detecting unaligned events. We also show that our framework significantly improves the state-of-the-art result on two benchmark datasets. For more details about our method and also to see our code, please visit our webpage. And thank you for your attention.